Okay, equations of motion once again. They give us an object whose acceleration, meaning the second derivative of their position, is t plus 1. And we know if you integrate that, you'll get velocity, because that's the first derivative of position. And if we integrate that, we'll get position, s or s of t. So we need some antiderivatives. Velocity is the antiderivative of t plus 1 dt, which is 1/2 t squared plus t plus a constant. Uh-oh. Technically, we could do the antiderivative of this while it still has the c in it, and we'd get ct plus another constant, but I generally prefer to knock these off as I get to them. They tell us up here that the initial velocity is 0, meaning when t equals 0, v is 0 also. Knowing that, we can put in 0 for the t's and we get velocity equals 1/2 of 0 squared plus 0 plus c. Soon enough we find that that first constant is 0, so nice. It's 0, I'm just going to throw it out. In this case, you could have forgotten about the c and you would have gotten away with it. Unless this was a written response question, in which case I would have jumped all over you for not putting the c, but better that you put it in and then check it and find that it's 0 rather than hope to get lucky. Now that we have the velocity, we can do another antiderivative of 1/2 t squared plus t dt, and that'll be our position. So that'll be power of t goes up to 3, divide by 3, so we get 1/6 t cubed plus 1/2 t squared plus c again, another constant. And they tell us the initial displacement was 0 also, so if t is 0 again, we get 0 and 0, and okay, they're going easy on us with this one. Both of the c's are 0. So that's our acceleration, that's our velocity, that's our position function, and yeah, that's all they wanted. They want an equation representing the velocity. There it is. That's our first derivative. And the displacement, which is our 0th derivative, or the function before we've done any derivatives. It's just a matter of integrating back.